Swayam Prabha. Digital India. Educated India.
Okay, in the last few classes we looked at the detailed derivation of the Rayleigh-Jeans distribution followed by the Planck's distribution, and which led to the birth of quantum mechanics, and then we saw some special asymptotic limits of the Planck's distribution which led to the Wien's distribution as well as the Rayleigh-Jeans distribution. Then the d by d lambda of the Planck's distribution, equating it to 0, we got lambda max T is 2898 micrometer Kelvin. So we solved it for some x plus, the x plus was 4.965 when we solved it using successive substitution. So this lambda max into T is 2898 is called the Wien's displacement law, because the lambda max is equal to 2898 divided by T. As T increases, the lambda max shifts to lower values. In fact, even without that, if somebody consistently made some good observations of IB lambda for various temperatures, visually you could have located the optimum and you could have joined using a straight line, you would have figured out that lambda max into T is 2898. However, from the Planck's distribution this can be mathematically derived. Are you getting the point? So in fact we saw that actually if you replace the variable lambda by lambda T, you get the whole thing, the IB lambda becomes a function of lambda T only, and all the curves, that is all the curves corresponding to different temperatures, collapse into one curve that is called the universal blackbody function. I think we stopped at this stage. In between we also integrated the Planck's blackbody distribution, and we got the Stefan-Boltzmann's law, we got the value of sigma, and that integral turned out to be pi to the power of 4 by 15. Of course we did not check it, but now you are doing your assignment and you are checking it using quadrature and trapezoidal rule and all that, integral x cube d integral 0 to infinity x cube dx divided by e to the power of x minus 1. So that will be pi to the power of 4 by 15. You will get a value which is numerically very close to this, pi to the power of 4 by 15. Okay. So one of the most important things is it is the quest for determining the blackbody radiation function which led to quantum mechanics. That is very important, and the best minds, it was challenged by the best minds in physics 100 or 150 years back. Now towards the end of the last class I introduced this concept of universal blackbody function. So IB lambda, when I say IB lambda, it is implicit that it is Planck. Okay. So C1 so we divided IB lambda by sigma T to the power of 5 T to the power of 5. Okay. See, there are some variants to this. Okay. You can divide IB lambda by T to the power of 5. Watch carefully. You can divide IB lambda by T to the power of 5. You can also divide EB lambda by T to the power of 5. It will give the same thing, except that it is a scaling factor. What is the relationship between E and I for a black body? There will be pi. So you can divide IB lambda by T to the power of 5. You can divide EB lambda by T to the power of 5. You can divide I lambda by sigma T to the power of 5, or EB lambda by sigma T to the power of 5. So do not get confused. Suppose you take different books, may come out with different expressions for this. So it will be into 10 to the power of minus 13 into 10 to the power of minus 6, 7, whatever, depending on how it was divided. But essentially the funda is it is divided by T to the power of 5. All the other things are constants. When you divide it by T to the power of 5, all the curves collapse. So you have, so let me say now it is EB lambda by sigma T to the power of 5. I am allowed to do this. Okay, I am allowed to do this. So if it is, no, it not be like this. That will be the shape. What will this be? 2898. Okay. Now all the time we are not just interested in finding out what is the total area under the curve from lambda is equal to 0 to lambda equal to infinity. Sometimes we are interested in finding out how much of energy is up from the how much of energy in the visible part of the spectrum is absorbed. Okay, how much of energy is absorbed in the infrared part of the spectrum, or I have a satellite orbiting the earth, let it be put in a geostationary orbit, that will be at a height of 36,000 kilometer, it is stationary with respect to the earth, it is always looking at India. I have an instrument, an infrared imager or a sounder which captures the radiation coming from the earth's surface, which is altered by the clouds, rain and all that in the atmosphere. Now this instrument can be a multi-frequency or a multi-spectral instrument, that is, it is capable of capturing the radiation in different frequencies. Those frequencies are chosen based on the electromagnetic spectrum, where the atmosphere absorbs, where the atmosphere is transparent and so on. So a particular instrument may have frequency response in various channels. In each channel you cannot have a direct delta function, are you getting the point? It cannot have 100, are you getting the point? Around a particular lambda is equal to 4.5 micrometer, it is not that at 4.4 or 4.6 the radiation which is captured by that instrument will be 0, are you getting the point? Generally it will have something like this, right? Suppose this is 4.65 micrometer, there is no device on the earth which an engineer will make which will have a frequency response like this, that is the response of the instrument. So generally it will have something like this, are you getting the point? Around this lambda or nu there will be a d nu associated with this, therefore there will be a small band, there will be a small range of frequency lambda over which this instrument will respond. So we have to capture from lambda 1 which is left of this, so you have to capture from lambda 1 to lambda 2, therefore we are interested, therefore are you getting the point? So this area under the curve will be the total energy, radiation energy which is captured by any instrument. Therefore now we are interested in what is the energy which is captured in some portions of the spectrum. I am trying to establish the need for doing that. Therefore we are also interested in knowing what is the fraction of the energy, what is the energy which is absorbed or transmitted or reflected whatever between lambda 1 and lambda 2. Therefore at will I will say from this lambda 1 to this lambda 2 it is a black body. Can you tell me out of sigma t to the power of 4 how much fraction is there? Are you getting the point? Therefore we are interested in finding out this one. So if this is lambda 1 and this is lambda 2, we are finding out, we want to know what is this shaded area. From 0 to infinity the shaded area sigma t to the power of 4 if you take EB. Out of that if I know the fraction I can multiply it by sigma t to the power of 4 for a body at a temperature T, and then I can get so many watts per meter square in this wavelength band. Okay. Therefore I need to work on this fraction. So this is called f function. So this f function is f of lambda 1 to r okay. What is the fraction? What is the fraction of energy emitted by the black body between the two limits lambda 1 and lambda 2? I am not putting T1 and T2, watch, because it is for a body at a temperature T. You can put T1 and T2 with the understanding that T1 equal to T2 equal to T. Okay. Now this I will say that is f from lambda 1 t to lambda 2 t is equal to f of 0 to lambda t minus f of 0 to lambda 1 t, right. If I have a way by which I can calculate this area first and then subtract it to this area, then I have this. Okay. So if I have a formula or if I have a table, if I have a lookup chart which will give me f of 0 to lambda for any value of lambda, the problem is solved. Okay, between 0.4 to 0.7 I will take lambda 1 is 0.4, lambda 2 is 0.7. You tell me the temperature, I will multiply lambda 1 into T, lambda 2 to T. If I have a first column lambda 1 T and the second column if I have this fraction, I have essentially solved the problem. Mathematically this is so f of 0 to lambda 1 t correct. So this fraction is the total energy in the band 0 to lambda 1 t divided by the total energy in the band 0 to infinity. So f is a dimensionless number which varies between, okay, so 0 less than equal to, we call it as the f function.
Particular wavelength, right? So why are we still hanging on to lambda 1 t? Why lambda t?
Lambda t because it is universal. I can make one table. Otherwise, I have to do for different temperatures. Lambda it is not good. If you don't like any of this, you can just use the Planck's distribution, find out lambda 1, lambda 2. You can work with that also. This is to make it easier. That's all. Because that is why I introduced the universal black body function first. His question is, why are we hanging around with the t? My point is, if I multiply lambda by t, then there is only one curve. I can have just one compact table with which I can figure out. Therefore, the fraction of energy will be we can't say fraction of energy emitted, no? Is given by f of it does not matter whether the f of lambda t has taken care of I lambda, E lambda, all, because numerator and denominator all the constants will get cancelled. Multiply by sigma t to the power of 4 is the key point. Are you getting the point? No. Okay. So the first one is 600, and for example, if you look at 600 and micrometer Kelvin, you get 185 into 10 to the power of minus 18. So, but this is basically, so this is EB lambda divided by sigma t to the power of 5, okay. So if you see, this value keeps going up with lambda t, okay. So 2898 it becomes a maximum, right. When it is 2898 it becomes a maximum, that corresponds to the Wien's displacement law, correct. Now it goes up and right. So this is that yeah. So this is watts per meter square per micrometer Kelvin to the power of 5. The last column gives you f of 0 to lambda t. Last column gives you f of 0 to lambda t, okay. That is the important thing. So you can see that now I am not able to show everything on the, let us see. So what should be the maximum? So when it is maximum it is around, no, yeah, it will reach the f fraction will reach 0.99, we will stop with 0.99998, okay. So this is a very comprehensive, you can use it to your advantage, you can use this table intelligently, you can in fact get watts per meter square for the whole thing, and you can do a lot of things with this table, right. But it is very useful to solve problems where I ask you to find out what is the total energy emitted in a particular wavelength band. For example, solar energy, okay, we considering the outer surface of the sun to be a black body at 6000 Kelvin, standard question will be what is the fraction of the total energy emitted by the sun which is in the visible part of the spectrum? That is a very standard question. Okay, like that you can, for different bodies which are emitting radiation, which are at different temperatures, you can get an idea of the fraction of the radiation which is emitted in a particular wavelength band, near infrared, far infrared, ultraviolet and so on. This is okay. Now we will do some work in Excel. Now I can just put X close. Okay. Over. Yeah. Now is this clear? Now the first column is lambda into T, okay, corresponding to 1200. There was some 0.99, right? It was 99 or something in the table, correct? Corresponding to 1200. .9 is 93, yeah? Okay, so okay, 1400 is 2.39, right? And then 1800, I have done all that. Up to 6000 I have gone. What is 6200? If you want I can add 6400. Okay, how much? What do you get for 6000? Okay. Now you see this is the universal black body function with lambda max. Are you getting the point? The maximum is about 2898, it corresponds to this. So I am able to plot this, right? So from that table you can replot and confirm that you will get a universal black body distribution function, right? And the fraction is also given. Now we will solve a problem which will cement all our ideas about IB lambda, Wien's displacement law and F function, everything, right? So please take down this problem. Problem number 7, 8, 9, it's only 6, huh? What is the problem number? It's not 1, right? 5. Problem number 5. Consider a black body. Problem number 5. Consider a black body at a temperature of 6000 Kelvin. Determine the following. Consider a black body at a temperature of 6000 Kelvin. Determine the following. A. IB lambda at 0.4 micrometer. B. IB lambda at 0.01 micrometer. A. IB lambda at 0.4 micrometer. B. IB lambda at 0.01 micrometer. C. IB lambda at 10 micrometer. Okay, C. IB lambda at 10 micrometer. D. Total hemispherical emissive power. D. Total hemispherical emissive power. D. Total hemispherical emissive power. E. IB lambda corresponding to lambda max. E. IB lambda corresponding to lambda max. F. Ratio of IB lambda at lambda max. F. Ratio of IB lambda at lambda max to IB lambda at 10 micrometer. F. Ratio of IB lambda at lambda max to IB lambda at 10 micrometer. G. Fraction of the radiation in the visible part of the spectrum. G. Fraction of radiation in the visible part of the spectrum. So if you have to complete all the parts, it will take 10 minutes, but it will reinforce all the concepts, all the formulas which you have derived, right. So I will quickly go through the problem again. Consider a black body whose temperature is 6000 Kelvin, determine IB lambda 0.4 micrometer, 0.01 micrometer, 10 micrometer, determine EB, determine IB lambda corresponding to lambda max, IB lambda max divided by IB lambda 10 micrometer, that is part F, and part G, fraction of radiation visible part of the spectrum. If you do not have calculator, you can still manage with the F function chart I have given, okay, or you take out your calculator and do it. Is that okay? This will give you EB lambda, so you have to divide it by pi, okay. Even then I think sigma t to the power of 5 you require the cal C. For the sake of completeness I will write it on the board, you just proceed. I am writing the question again. Okay, this is the problem statement. For the sake of completeness and for the sake of NPTEL, I have written it. Okay. Now, part by part you can solve this. So, you will get a feel for this C1, C2 and all this. So, what I will normally do is I will first calculate lambda t and I will calculate C2 by lambda t and get e to the power of C2 by lambda t minus 1 and keep it. Otherwise, when I do in there is a minus 1 and all that, there is a chance of making mistake. So, I will proceed from the denominator. Maybe you have a better way of doing. So, this is the way I will do it. I will just calculate lambda t first, divide C2 by lambda t and have that ratio, then raise it e to the power of that minus 1 and first figure out the denominator. I want to use this, I want to retain this because the next half. Shall I erase this? Now, that minus 1 is not on C2 by lambda t, minus 1 is on e to the power of C2 by lambda t, okay. You can use this, no problem. Then, but sigma t to the power of 5 you have to multiply, divide it by pi, so many things are there. that is EBT, no, it's not. Yeah, Pranay, what's the matter? No calci? Finished?
Second
Okay, what is the answer for the first one?
2.91 10%.
10 plus 7? Correct? Correct? Okay, no, maybe it's correct. 2.97 into
10%.
yeah, units. Watts. Watts per meter square. Micrometer multiplied by radian, correct. Because IB lambda is the flux around the d lambda about lambda around a in elemental solid angle d omega about omega in the theta phi direction. An elemental solid angle d omega in the theta phi direction. We drew arrows and all that, we spherical coordinate system, we did all that, right? Fine. For 2.91 10 to the power of 7. Yeah. Similarly, we can work out the other things. We will just start writing the answers. Yeah, 2 point. Pranay, 2 point into 10 to the 7. Okay. This fellow is 0, no? He is 0. The calculator shows error, right? That means he is too small. You don't have to worry. So there is hardly anything in that part of the spectrum from the sun. Okay. 10 micrometer infrared. What is this point? Not one is ultraviolet, right? Correct? From the ultraviolet part there is nothing much. Actually it will be insightful if you look at all this and work out, and you can learn a lot of things by working out problems. Okay, 10 micrometer. 42? Yeah. EB of T. What is EB of T? Sigma T to the power of 4. Srikanth. So the power has come back. Correct? EB is how much? It will be high. 5.35? 7.35, 10 the 7. Huh? 10 the? Watts per meter square. What is lambda max? Point? What is the beauty? What does 0.483 micrometer correspond to? Visual is okay. Blue. It corresponds to blue light. So the funda is the maximum in the solar energy. Of course, there will be a small change for if you want to do solar radiation, you won't do 6000 Kelvin. You may use 5800. But that will also, because blue is 0.45 to 49. Okay. So blue light is very important. Okay. So this is blue light. That is very important, right? Blue light. Maximum is in the blue light. Now, what is IB lambda corresponding to that? You already have that fraction in the table. It will be just above this. It will be just above this. So in the first quiz, if I ask a question like this, how long will it take? For say 7 or 8 parts. You want such a question? It's too simple, right? First question I will give something like this, but not 6000 Kelvin, okay? So it will test your basic fundace, whether you understood all the formula, okay? Some 5 marks we can give, or 8 marks. What do you say, Ganesh? Samarjit, tell me. 3 into 10 to the power of? Fine, 3.4 into 10 to the power of 7. What is this? Huh? No. IB lambda corresponding to lambda max divided by IB lambda 10 micrometer. It's a huge number. Correct? Pawan, what is that? 7,476. So, it's a very important result. The IB lambda corresponding to visible blue light divided by the IB lambda corresponding to the infrared at 10 micrometer for the temperature of 6000 Kelvin, which corresponds to the outer temperature of the sun. You can see that visible to infrared the ratio is 7,476. Okay. Now let us do the last part. Okay, is this fine? Okay. So the visible part of the spectrum is 0.4 to 0.7, T is 6000 Kelvin. Okay. Now no, that is not correct. Okay, now can you use the table? Can you focus on this? Okay, now so we have to corresponding to, we used to have a so 2400, so corresponding to 2000 no, point 14 point 14, so that is corresponding to 2400. Okay. Now corresponding to 4200, $516, correct? It's 516. Okay. What are those two numbers? Point 24, 0.516. Three. Please do not underestimate the importance of this result. I come again, please do not underestimate the importance of this result, because 0 to infinity is so huge, 0.4 to 0.7 is so small, but f of 0.4 to 0.7 is nearly 40% of 0 to infinity. So 40% of the solar radiation is concentrated in a very small part of the spectrum, the visible part. That is why we are all happy. We are having daylight and this thing, we want to reproduce all these lights, even during night we want to have this white light and this effect we want to reproduce. That is why, because of this only, because of this particular temperature, it is so habitable. Everywhere it is too dark and this thing, and or if the temperature is such that, if the temperature of the sun were to be different, we may have the peak at some other part of the spectrum, we may not get enough radiation. Huh? Come again? We would have evolved differently. I do not know whether we would have evolved differently or. So it comes back to that, so it begs the question. So if now we have this, if we have a temperature of the solar system now to be 6000 Kelvin, which makes the earth so habitable, therefore when the Big Bang theory, it started with basically it is all a cooling problem or a heating problem, whatever. So it started with some initial condition. So if the initial condition were to be different, then the temperature of the sun today would have, outer temperature would be different, which means the fraction of the radiation falling would be different. Therefore we may not be there, there may be no NPTEL course, I may not be there, you may not be there. Why was the initial condition chosen that way? Who chose the initial condition? Is it the act of God? It could have been different. What is that? Okay. So, Srinidhi, you did not get it. They are saying it is the act of the robot. Which robot? Okay. So, therefore, you can link it to our basic question. Why is the temperature like this? And then, so it follows a certain cooling rate, water. Okay, we can write equations, but who will give the initial condition? There was an initial condition, suppose. Why was this initial condition given? Who gave this initial condition? We do not know. Okay, fine. Now, so this is an important result. So about 40% is in a very narrow range of 0.4 to 0.7 micrometer, and the peak is also embedded in this around 0.48 or 49. Okay. Deepak has a question, are the ratios of IB lambda and the F same? They will not be the same, because F is an integrated quantity, correct, between two limits, 0 to that particular value of lambda. Okay. Now so far we were hung up on this black body, okay, but we know that there is no black body. I mean the black body is a concept, because there is no perfect black body which absorbs all the incident radiation, and by virtue of which it will be the perfect emitter. Real bodies are neither perfect absorbers nor perfect emitters. So there is a departure, or there is a deviation or departure from black body behavior. However, as engineers we have to live with real surfaces. So if I already know upfront that real surfaces are not black bodies, I need to characterize their behavior, that is characterize their behavior with respect to radiation. Therefore we have to introduce a concept of radiation surface properties. Okay. What is the goal? To characterize and quantify departure from black body behavior. So this departure from black body behavior manifests itself as incomplete absorption. So there could be, there is imperfect absorption by virtue of which there is imperfect emission. Now we have to characterize. Now let us look at some surfaces which depart from black body behavior. Enough? Maybe you require some more. I will project this also onto the screen. I think this discussion cannot be completed. Is it okay? I stay with this or I open with this fine, okay. Figure 2 is not good, man. First we start with figure 1. Okay. Okay. Please look at figure 1, figure 2 back to back. Hey, did you get Tejas? Not over, I have enough. Here, Pradeep. Here, everybody got it? Okay, let us look at figure 1. So this is spectral intensity. You will worry about later whether it is IB lambda by sigma to whatever versus wavelength. So this is for a black body at 1073 Kelvin, which is about 800 degrees centigrade, which is a temperature normally encountered in engineering. 800 degrees centigrade is not a temperature which is impossible in engineering practice. Okay. So from you can draw the IB lambda. You also know the peak with 1073. The maximum will be around 2898 divided by 1073, about 2.8 micrometer, which is consistent with our. So funda 1. This black body distribution is correct. Okay, so that is the first one. Black body at 1073, but you could have a body corresponding to curve A, which is called a grey body at 1073 Kelvin. A grey body at 1073 Kelvin is a body the ratio of its emission at a particular wavelength, the temperature of the body is fixed, do not worry about temperature. There is a body at 1073 Kelvin, okay. IB lambda will vary with lambda, right, according to Planck's distribution. So the I lambda also varies with lambda. If somebody measures I lambda and you for that temperature you get the corresponding IB lambda from the theoretical Planck's distribution, it is a dimensionless ratio which is varying between 0 and 1. Because no body can exceed the emission of a black body, but I am saying that there could be a body where this ratio is independent of the emissivity, independent of the wavelength, okay. So such a body is called a grey body. That grey body is an idealization, but still we want to use it because it helps us simplify calculations in radiative heat transfer. Otherwise, if you want to consider this ratio as a function of lambda, the analysis becomes more and more tedious. Go to curve B. The curve B is indeed the behavior of most real surfaces. It will be like this, okay. The curve B is like this, so you can figure out that radiative analysis of a surface which follows B is a lot more difficult than a surface which follows the behavior A. But still the area under the curve for A and B may be more or less the same. But if you use the gray body assumption, that is you have a smooth curve, it may lead to some errors in the local this thing for a particular value of lambda. When you are finding out this I lambda, it may differ, there may be some error, but if you average out, if you are integrating from 0 to infinity, it may be, or from a lambda 1 to lambda 2, it may be, the error may not be much. Okay sir, why do you want to use this? Because for most surfaces I lambda versus lambda is not known for many surfaces, that is this ratio is called the emissivity. I will come to that, I do not want to formally introduce in today's class. This ratio is called emissivity. If it is a function of the wavelength, it is called a spectral emissivity. Spectral emissivity of most surfaces is unknown, therefore we may go for a gray body behavior, point number 1. Point number 2, spectral emissivity is known, but you do not have the fundas to put it in your analysis. That is generally the case, somewhere in some reference or somewhere it may be there, some data book somewhere it may be there, but do you have the competence to put this spectral information and do your radiative transfer calculation? Very few people in the world can do that. Therefore, because of these 2 points, either because the spectral information is not known or you do not have the competence to handle that spectral information, people going for a simple assumption where I lambda by IB lambda is not a function of lambda, that is called a gray body. In tomorrow's class, if I lambda is not a function of the angle, then it is called a diffuse surface, that is figure 2. We will discuss that diffuse surface tomorrow and formally introduce all these properties one by one. We will get into the math and then subsequently we will solve lot of problems with epsilon lambda, epsilon theta, all that, and logically it will come to finally that global emissivity called epsilon, which you abused left, right and center in basic courses, epsilon sigma t to the power of 4. I will tell you that story that epsilon has got a long and tortuous this thing, right, you have to do so many integrations to get that epsilon. Okay, we will stop.